This is really a pleasure to be here, and it's felt from the heart, really. So yeah, so Enzo contacted me when the idea of this school started to talk about philosophy of dark matter, and I told Enzo, well, I don't work really on dark matter, but I wanted so much to come back and enjoy the nice atmosphere. And so said, oh yeah, but you worked on something related to dark matter. And saying yes, okay, yes, there is something I have been working on that is related to dark matter. So my main research is in quantum gravity, and by the end of these lessons, I'm gonna tell you how I see a possibility to connect the research on dark matter with the research in quantum gravity. And the connection comes from primordial black holes. So, let's see. Okay. So it all started with a project of mine regarding black holes, quantum effects on black holes, and this was in 2014. And in 2014, that is at the end here of this graph, where you have the number of papers on primordial black holes since when the idea was proposed. Well, actually, when one of the first paper on primordial black holes appeared. Well, in 2014, there were not so many papers. It was a kind of an underground idea. So for me, it was very exciting. It was very easy to become an expert on the field because there were very few papers to read. So this was 2014. And then 2015, suddenly, the number of papers became 4 times what they were before. And by now, we have quite a huge amount of papers on primordial black holes. So, and I couldn't keep up. So I'm very sorry if I'm gonna so I'm gonna give you a flavor of the research that is going on and give you a bit of history, where this idea come from and so on, but it's impossible to keep up with all the different papers that are appearing. And so the plan for these lectures is to tell you a bit about the history, tell you about what are the peculiarity at the conceptual level of the idea of primordial black holes. I will try to give you an idea of what are the current directions, in particular in relation with how these objects may form. And by the end of the lectures, I'm gonna talk more specifically about my research. So a specific kind of primordial black holes that are those that are already into their afterlife, I would say, in the form of remnants. And so I will focus for my last lecture completely on this. So that's the plan. And how are black holes and primordial black holes connected with dark matter? Well, you can think that they come into this big class of objects that are called machos. So macho stands for massive compact halo objects. And there could be many different objects that fits into this category. For instance, if there are failed stars or other objects that don't emit enough radiation to be observed. So all those objects fall into this large category, and black holes can also be part of this large category. What is peculiar of MACHOS is the fact that it's a proposal for dark matter that relies somehow in known physics. It doesn't require new physics, or better, we will clarify this in which sense you may need a new physics, but it's new physics of the kind that we would expect. We don't need to construct a completely new theory in order to fit this scenario. And this is to be compared with another big class of objects that may constitute dark matter, that are the WIMPs, the weakly interacting massive particles. You are having a lot of lectures these days about dark matter as coming from particle physics candidates. In this case, you need, in most of the cases, new physics, some kind of exotic physics. Maybe exotics, I just mean something that goes beyond the standard model and goes beyond the fundamental forces as we know them today. So I will concentrate on the first category, the MACHOS, in the form of primordial black holes. And of course, it's possible that MACHOS and WIMPs coexist, even though we will see that there are very strong constraints on their coexistence. And I would like to focus, since it's a philosophy school, I would like you to keep in mind this distinction between explanations for dark matter that are kind of conservative, that requires just the standard physics as we know it, and theories that requires new physics. And how do we evaluate this? I mean, we heard from Saskia before, is maybe the novelty an element that will give us more credibility, more confidence into one research direction rather than the other? Well, we can also argue for the opposite, right? But this, let's keep this in mind for the end of these lectures, when we will try to wrap up together the information that I'm going to give you about primordial black holes. So, well, of course, if you are a student of physics and you know nothing about the observations, the evidences of dark matter, and somebody tells you what could dark matter be, well, I suppose naively the first answer would be, well, could they be black holes, just black holes? Black holes are objects that interact only gravitationally. They don't have electromagnetic emissions, but for, of course, the accretion disk and possibly Hawking radiation. But by themselves, when they are in isolation, they don't, and when we forget about our Hawking radiation, that is a phenomenon that has to do really just with the end of the evolution of black holes. Well, in those cases, you have just objects that behave like perfect dark matter. They interact gravitationally and nothing else. And so they are black. So of course, people tried to evaluate whether the black holes we knew could constitute dark matter itself. And the answer, of course, was that the expectation of the number of black holes was not enough to fulfill all the dark matter. So what were the black holes that we knew? Of course, the first the first way in which we know that we can form black holes is at the end of stellar evolution. So a star form goes through all its long evolution. You need the star to be big enough. By the way, remember that in the early universe, stars form has been bigger. So this is something that helps if you want then to make a black hole. They exhaust all their fuel. They go through all the chain of nuclear processes to the point in which they don't, the pressure cannot, the pressure given by a nuclear reaction cannot compensate anymore the gravitational pull. And then, of course, you have the formation of a black hole. We have evidences for them through X-rays observed in binary systems. And today also we have observations of gravitational waves that comes from the merging of black holes. Now, keep in mind that I was showing you this picture. So we have evidences today that that black holes are standard objects in the universe. This was not the case at the time in which dark matter was first discovered or understood that it was there. Black holes for very long were considered very exotic objects, possibly not even existing. People were doubting their existence. I remind you that if you look in the general relativity book by Weinberg, for instance, it's still written that black holes may not be real objects. So when we say that, of course, dark matter can be black holes, well, keep in mind that when dark matter was discovered, the presence of dark matter was considered to be required. Well, black holes were still exotic objects, let's say. And of course, another thing that changed in our understanding is that now we know that almost all galaxies have supermassive black holes at their center. And so you see, we go from the stellar black holes that have something between 1 and 100 solar masses to black holes that are 10 to the 6 to 10 to the 11 solar masses. So it's very interesting. So something to keep in mind is also this very large range of masses with that leads to different properties and different phenomenology. As an example of how big a black hole can be, 10 to the 6 solar masses is the amount of mass that there is in our in our galaxy, in our Milky Way. The quasars that we observe, so the active galactic nuclei, are something around 10 to the 8 solar masses, and now we have observed objects that are even bigger. So in particular, one of the biggest one was called TON, that was 10 to the 10 solar masses, and now we are, I think that there was recently a discovery of a black hole that was even bigger. So there is then a third category that are intermediate black holes. So everything that is in the between of the stellar black holes and the supermassive black holes. So between 10 to the 2 and 10 to the 5 solar masses. So while for the stellar black holes and the supermassive black holes, we have almost certainty about their existence, for intermediate black holes, there is still a quest to understand how many are there and how they form, but there is a mounting evidence. So I think that most astrophysicists would say, yes, there are also those black holes. So a full range of dimensions, of masses from the stellar one, so from those that are slightly bigger than our sun, above, of course, the Chandrasekhar limit, to a difference that is of 10 order of magnitudes in terms of the mass. And I was saying, something to keep in mind is the fact that the density of those objects is completely different. So we have this picture in mind that the black hole is a very, very extreme object where the energy density, is very, very high. Well, in fact, for stellar black holes, the energy, the kind of matter density that you need is the one of atomic nuclei. But if you think instead of these very, very large black holes, well, the kind of density you have there when you enter inside the black hole is comparable to the density of water. So in general, in order to form a black hole, you need some matter distribution that gets denser and denser, but you can play with scales. And it's not necessary to reach very high densities, because for certain black holes, you can have less density, but if you have a very large region with a lot of mass, you can also have a black hole. Keep this in mind. And so these are the black holes that we know, more or less. But within these categories, stellar, intermediate, supermassive, I would like to add a third one. So I said I'm going to talk about primordial black holes. What does it mean, primordial? We said that the usual story for the formation of a black hole is that there is a stellar evolution at the end of which, through gravitational collapse, a black hole form. So, of course, all the black holes that are bigger than the Chandrasekhar limit could be, in principle, be formed through a stellar evolution, through stellar evolution. But there could be other ways in which black holes forms, not necessarily at the end of the stellar evolution. And so I will put in a big category all the black holes that forms before the time in which stars lighted up in our universe. So in the history of the universe, you see here we have the first star that forms 300 million years after the Big Bang. So there is a very long time here in which other things could happen. And of course, if you believe quantum gravity, it's possible that there was also a time before the Big Bang in which things could happen. So if you think of black holes as being formed by stellar evolution, you need to wait at this time stars to form, and black holes can only form later in the history of the universe. So we wanted to consider a possibility that black holes may form before through other mechanisms. Okay. So, a bit of history then about this idea of primordial black holes. Well, the idea as it's often the case in physics, came first from Russian scientists in the 60s, Novikov and Zeldovic. So if you, yeah, there is a joke that whatever you came up in physics, there is always some Russian physicist who did it first. So, so with primordial black holes, this is definitely the case. Even though Novikov and Zeldovic came to a conclusion that now we think it's wrong, that primordial black holes were excluded. So at the time, the idea didn't take a fly somehow, because the proposer themselves were thinking that it was not viable, so that there were constraints from known cosmology because of which primordial black holes would be present. And the idea and the viability of this idea was discussed later by Hawking and Carr. So at the time, Carr was a PhD student of Stephen Hawking. Bernard Carr is here and now he's an emeritus professor, of course, time passes. But he's still working on primordial black holes. That's imagine an entire life all working about primordial black holes. In fact, so in my lecture today and tomorrow, most of the references will come from Bernard Carr papers and reviews. So if you want, the modern history of primordial black holes indeed started with this 1974 paper by Hawking and Carr. And the idea they proposed, that is still today the simplest possible model to form a primordial black hole, is that primordial black holes may form because of the presence of cosmological perturbations in the early universe with enough density contrast. So tomorrow we will see that there are several different mechanisms that allow for the formation of primordial black holes, but I would say that this is still the most discussed one, the simplest, and the one that needs to be explored the most. So what's the idea? The idea is that in the early universe, you have fluctuation of the energy density. So the universe is on average homogeneous and isotropic, but you have these fluctuations that are the one that then evolve and gives you the power spectrum that we observe in the CMB and so on, and that we needed to explain with our cosmological models. But so when you study cosmological perturbations, then a peculiar feature, one of the way in which you determine the evolution of these perturbations is the relation between the perturbations and the cosmological horizon. So when these perturbations evolve, they may exit the cosmological horizon. And once they do that, they stop to evolve. They are like frozen. And then they may, depending on the way in which the universe evolves, depending on the different cosmological model that you may construct, you may have a different behavior such that perturbations may exit and re-enter the cosmological horizon. So, and this is what defines the characteristics of the power spectrum at a later time. And so so most of the model building in cosmology is exactly to fit almost scale invariant power spectrum using this mechanism. What about the formation of black holes? So you see here you have the perturbations that are in blue, and in the moment in which the perturbations enter the cosmological horizon, like you see this, there is this perturbation that enters here. So you may have the formation of a black hole by the direct collapse of radiation. So we are in the early universe. The universe is hot and dense. Basically, the universe is all constituted by radiation. And so you have this sea of relativistic particles with fluctuations. And in the moment in which the perturbations re-enter inside the horizon, you can have a gravitational collapse that leads to the formation of a black hole of the same size, basically, of the horizon itself. This means that as the universe evolves and as the cosmological horizon gets larger and larger, then in principle, you can form bigger and bigger black holes. So when the universe is young and small, you may have the formation of very teeny black holes. And the only constraint, so the constraint is given by the smallest possible size of your cosmological horizon. This could be as small as the Planck scale. So in principle, you can form Planckian black holes there. And then, so you have the cosmological horizon that expands, and you can have larger and larger black holes that get formed. Of course, you need a minimal density contrast. That means that, so where do I have it? Okay. Well, before I go to this, let me go here. So here you have the history of the universe, in which suppose there is inflation, like in the standard model of cosmology. You have inflation, then you have a period of reheating. You have a period in which there is radiation domination, matter domination, and then finally the current cosmological constant domination. And the Hubble scale is what define the horizon scale. So we can have different physical scales that are achieved through as the universe expands, and the formation in correspondence of primordial black holes. Of course, in order for a black hole to form, I was saying that you need a critical density that is a certain ratio with respect to the current universe, the current density of the universe at that particular time. So we talk about a density contrast for this ratio, and the density contrast at the beginning, it was thought that it was needed to be very, very high. And in fact, now we understand that this density contrast is just 0.5. So it's something that is totally achievable within primordial fluctuations of the matter density. Okay, so how likely are then primordial black holes to form? Well, this needs to be evaluated with respect to the fraction of patches that collapse within a given horizon. So in what you were seeing before, like here, we had possibly different patches of the universe. And within each patch, you want to know what's the probability for the black hole to form. And of course, you need the density contrast to be above a certain value. So this means that there is only a little fraction of, so the formation of primordial black holes corresponds to this part of this Gaussian distribution. So it happens here at more than 10 sigma. That means that indeed the formation is rare. But so depending on how this distribution, depending on the shape of this distribution, you can have the formation of more or less primordial black holes. So this means that if you have a mechanism that changes the shape of this distribution, then of course you can tune, you can have a way to tune how many black holes you form in the early universe. And I just want to mention, as an example, there is a process that is called quantum diffusion, and this could make the details here of this distribution shallower. So tomorrow we will see more mechanism for the formation of primordial black holes, and we will see exactly how different models may increase the formation of primordial black holes in order to fit the parameters, to fit the amount of dark matter that we want, and the kind of masses that we are interested in, and so on. So, of course, for the bad and for the good in cosmology, there are a lot of parameters to play, and this is what cosmologists are doing these days, producing these 300 papers per year, basically. So something interesting to keep in mind is that in order for the formation of a black hole, so you need a collapse, and whether there is a collapse or not depends on the question of state of the universe. So before we were seeing in this image that, well, the question of state of the universe changes in the sense, so the question of states is given by the ratio between pressure and density, and if you have radiation, you have more pressure. So as the content of the universe changes through its evolution, you have a change in the equation of state. And if you have, so there is there are competitor mechanisms, because the more pressure you have, the more radiation you have, the less you can form primordial black holes, right? So this is something to keep in mind. So when we look at the thermal history of the universe, so you see here in this diagram, you have the degrees of freedom that behave in a relativistic manner, so they behave as radiation. And you have the temperature, so the universe, as it expands, it cools down. So this means that it goes from being very hot here, right, to be cooler and cooler in this direction. So as the universe cools down, the kind of particles like top quark, the WZ, and so on, all these particles stops to be relativistic, so to the point that you have less and less components of the matter content of the universe that behave as radiation. So So this gives an equation of state of this kind. And you see where the equation of state it's like this with like in this point, you have in correspondence the possibility to form more primordial black holes. So what you see in this diagram is the possible fraction of primordial black holes in different masses. We go from very small black holes to stellar black holes here, like a solar mass is here, 10 solar masses, and so on. And so given the thermal history of the universe, we could expect this kind of peaks. And these peaks indeed corresponds to observations, for planet or even less satellite sites, black holes that may be observed with microlensing. We can have a peak that corresponds to the observations done by LIGO in the merging of black holes. And we can have also a peak here that corresponds to supermassive black holes. So again, if you trust this, this idea, you may have with a single explanation a possible fit of different observations, different features that are currently observed with at different scales. Again, going from microlensing to explaining providing the seeds for supermassive black holes. So the idea could be that supermassive black holes, the black holes that we have seen being so large, being, what was it? 10 to the 6 to 10 to the 11 solar masses, they may have indeed an origin directly from primordial black holes. Okay. So let me go directly to the main question, because so what are the constraints? So this, I gave you a bit the flavor of the history about primordial black holes. This so far seems to be appealing, but what are the constraints? So the current constraints are here. I will discuss this in more detail later, but I think this is an extremely interesting case from the way, from the history of physics, for the way in which the credibility of a theory works, in the sense that primordial black holes have thought to be excluded, and then they came back in fashion again, and then they were excluded, and so on. So, I mean, I think that if you have been around, people that have been around for some times and may have heard about primordial black holes before, may have heard simply that they were excluded by some observation. Well, there are some caveats, and constraints today have been revisited, and some of the constraints have been understood not to be really reliable. So in particular, here in this graph, you see some dotted constraints, like this one, and those are constraints that we don't believe anymore. So again, I wanted to go later maybe in the details of what gives this kind of constraints, but let me just tell you what it is. This graph is a graph in which you have different possible masses. So remember, a solar mass is 10 to the 33 grams, so it's here. So solar mass is here. Everything that is below the solar mass is here, and supermassive black holes, we say that they are around here, but we are considering, you see, black holes that could be even larger and larger. And then, so we have a constraint that comes from above here. There is this peculiar constraint. What is this constraint? Well, this constraint is that if you have all the dark matter that goes into a single black hole, you started to have a problem of credibility. Like if you started to have all the dark matter being in just a single black hole, if you go beyond this this scale, you may have less than one object in a single galaxy, and of course this will go against the observation. So you need some dark matter in your galaxy, at least one of these black holes, right? So this is why there is this line here. But again, here we are at 10 to the 45 grams, and we say the supermassive black holes are just here. So this is really a scale that is not so credible or interesting. So we are more interested in all the space that there is here. So how this graph works? This is the fraction of black holes that could be dark matter. So this means that you imagine that all the dark matter is all appearing in a single mass, okay? And then you check what are the constraints for all the dark matter to be primordial black holes of that particular mass. So you see that, so if you have a 1, it means that all the dark matter can be black holes of that particular mass. So, and then if you go here, it means that only 1/10 of or like for instance here, you have that in the case of black holes of mass 10 to the 27, I don't know, black holes could be only 1/10 of the total of dark matter. So this is how these are the current constraints, and as you can see, there is a big empty space here for black holes that are between 10 to the minus 15 and 10 to the minus 10. Well, sorry, this is in terms of, so here you have the scale in terms of ratio between in terms of solar masses, and here in terms of grams. But so here basically you have a big space for very small black holes up to the scale of a small planet or a satellite, basically. Of course, all condensed into a Schwarzschild radius. So the constraints that you see here are from Hawking evaporation. So 10 to the minus 15 is the size of black holes that if they formed after inflation, they would be evaporating today. So that's why we have this constrained space. Even though, so I don't want now to go into all the details of this because because I have more graphs to show you about this. But the point is that these constraints have been revisited many times. They have these days, with these 300 papers per year, they have been revisited. They are constantly revisited. And one of the major understanding was that these constraints were always coming with caveats, with assumptions. And these assumptions have been challenged. So changing the situation from having black holes being forbidden to having primordial black holes being viable. Again, to me, this is a very interesting case of the way in which science proceeds. What do we take as a falsification of a theory, and so on. So I want to discuss this more with you. Yeah, sure.
Is there a reason why
well, this so if primordial black holes have so if you have a good theory that form primordial black holes being present today in this mass range, yes, then then they are a viable candidate for dark matter. There are no. So intermediate black holes, so we said a solar black hole is here, okay? And intermediate black holes, so then we have 10 order of magnitudes to arrive to the supermassive black holes. So it's everything in the between here. And again, remember that these shaded gray region are now somehow not trusted anymore as being constraints. So there is space here, but I wanted to I wanted to discuss with you exactly what are the caveats for this how, yes. Sorry. Oh, yes. Well, it means that you have more black holes than what you need for making all the dark matter. Yeah. So, I mean, in fact, in most of the graphs that I have seen, the graph stops here. Yeah. Choice of the author to consider the possibility that you may have something that is even more. If there is, yeah, more mass than needed, I would say, yeah, I would say so. I don't know why they have decided to show it. Yeah, I mean, of course, I mean, this, no, I mean, this is just observational constraints. So there is no assumptions with respect to a particular gravity model. There are assumptions, of course. For instance, a point that I wanted to make is about the constraints on Hawking radiation and so on. But I wanted to, there will be more slides in order to talk about this. I just wanted to ask, since we started a bit late, how am I doing with time? And when did we started? Okay. No, I just wanted to check when is a good time to make a break. Let me just maybe, yeah. Okay. So maybe let me just say a couple of more things before we take a break. So scales. I want to talk about scales. Because so I told you that primordial black holes form at different times. So what is so different times means also different scales at which the black holes appear, and I wanted to compare this with the observations in the CMB. And of course, the CMB give us vice versa constraints, because you want the formation of primordial black holes not to interfere with the power spectrum that we observe, right? But the thing is that the scale of the CMB each is much smaller, so much less evolving than the scales at which primordial black holes would form. So it's the first thing to notice. And regarding the scales, something that I want you to appreciate as well is the fact that so as black holes forms as the universe expand, I wanted to connect with what I was saying before regarding the fact that you may have black holes with different densities, matter densities, and this is also what happens with primordial black holes. So you can start with the smallest possible black holes at the Planck sites that may form just 10 to the minus 43 seconds after the Big Bang. Then you have the black holes at 10 to the 15 grams that corresponds to black holes that basically have the size of a proton. And these black holes so are the one that would be evaporating now, and they are the one that forms at the time that is 10 to the minus 23 seconds after the Big Bang. Then we have an important class of black holes that may form at the phase transition. So when quarks get together to form the nuclear particles. So this happens for black holes that will have a mass comparable with a solar mass. And so this is again happening a very short time after the Big Bang. And the sites, the possible maximal sites that we expect from the formation of primordial black holes, it would be something like 10 to the 5 solar masses, and this would correspond to a time that is 1 second after the Big Bang. So we have this in the history of the universe. So this corresponds to things that would happen here. We want, if we consider a model with inflation, we want black holes to form after inflation, of course, because inflation would dilute them too much. So we wouldn't have enough density of these objects to be comparable with the observations of dark matter today. They will be just spread everywhere. Of course, let me remind you that inflation is not the only possibility for cosmological models. So we will also see this in the future lessons. But if we stay with the standard cosmological scenario, there is inflation. Inflation is here before all these processes take place. Before all these processes take place, and also the formation of primordial black holes is just a process that may take place very close after inflation. Okay, so an interesting aspect of this is that if black holes forms in, oops, there is a typo. Okay, so if black holes forms in the early universe at all these different sizes, it means that studying primordial black holes can give us access to a very rich phenomenology, because we may, so if we start from the smallest to the largest primordial black holes that could be formed. So with the smallest one, we can study critical phenomena. We can have a star that called dark matter. We can have a lot of effects, such as the disruption of some astrophysical objects because of the presence of these primordial black holes. We can have lensing, we can have gravitational waves, we can have effects for AGN. So this is the scale that is usually studied with general relativity. We can have we can have effects that has to do with high energy physics, so they with nucleosynthesis and the reionization time, and then of course we can we can also study. Oh, sorry, there is, yeah. We can also study. There is a typo in this. There are sometimes typos in this slide that I need to fix. Okay. Anyway, so with the primordial black holes, so we can study the effects that they may have with gamma rays, both at the galactic level and the cosmological level. And finally, we can also connect the study of primordial black holes with quantum gravity. And in particular, I am interested in the formation of Planckian remnants, but also people are considering primordial black holes in connection with extra dimensions and higher dimensional black holes. So in the moment in which you allow primordial black holes to exist, well, you have a full range of possible phenomena that could be influenced by them, by their presence, and that they could be studied. No, okay. So before concluding, before taking a rest and making a pause, let me just say that I think primordial black holes are extremely interesting, but there is no need for primordial black holes to be the only dark matter component. So in fact, you can study primordial black holes in correction with modified gravity models. So for instance, when you construct cosmological models, I mean, if you have a modified gravity theory, you may also, this could be a way also to tune the formation of primordial black holes, for instance. You can have WIMPs and have primordial black holes. Of course, the presence of WIMPs and primordial black holes together is a bit constrained, but in principle, this is possible. So I think they are an extremely good candidate of dark matter, and one of the reasons why they are also an extremely good candidate is also because they don't interfere with possible other candidates. Okay, so in the remaining time, I wanted to talk a bit more about constraints, and I wanted to give you a bit of some considerations, some general considerations about how to think about black holes, about primordial black holes as dark matter, and trying to discuss with you, try to understand why people have not considered them before more seriously. But I think it's a good time now to have, let's say, a 10 minutes rest. And are there any questions at this point? Or let's keep more questions for the end of this lesson. Okay, thank you. If everybody's here, let's start talk about constraints on primordial black holes. And yeah, I think this is, again, I think it's an interesting story, also a very telling story from the point of view of the history and philosophy of physics. Let's see why. So where do the constraints on primordial black holes come from? So you see there is a number of different directions in which we can look for phenomenology of primordial black holes and see for constraints. Of course, the first one is simply the omega, the amount of dark matter. So it's related to the question that there was before. Of course, if there are primordial black holes, you don't want them to screw the balance between standard matter and dark matter. So they should come in the good proportion. There are constraints from the CMB. There are constraints from evaporation, both because of the fact that if they evaporate, in principle, according to the standard story, they may disappear, but also because with evaporation, we may expect the creation of cosmic rays, such as gamma rays, and so on. So, and we have with evaporation the emission of radiation, and this can also have effects on the balance in the history of our universe with respect to, for instance, nucleosynthesis and effects on the CMB and so on. So, so there are constraints there. Most of the constraints today come from lensing, and in particular microlensing. So, well, you can use the lensing for both very large and very small black holes. You can have disruption phenomena. That means that the presence of an object like a black hole passing close or like even being captured by other astrophysical objects can disrupt these astrophysical systems, so like in the case of neutron stars or white dwarfs. It can also have effects on the cosmic structures. More constraints comes from gravitational waves. We will see more about this. And I said that there could be an interaction with between primordial black holes and dark matter particles. So what is expected is that if you have a black hole surrounded by WIMPs, for which you expect some kind of annihilation, so the presence of the black hole triggers more events, so you should have a spike of annihilation events for WIMPs. And this is, of course, constrained. This can give you also constraints if you don't observe these spikes. I showed you before, well, actually, I have shown you before this picture. So this is another picture that was just a few months before the other, in which you see how even in a couple of months, constraints are changing these days. And so I wanted to tell you more about how this graph for constraints is constructed. Something that I want you to appreciate is that the constraints come from different epochs. So we see them all flats here, but each constraint corresponds to a different period in the history, in the evolution of the universe. So we should be careful with that. Another important consideration that I wanted to mention, that I wanted to mention at this point is that constraints change depending on the way in which the masses of primordial black holes are distributed. So this is the first caveat with respect of all the constraints on primordial black holes. So all the constraints on primordial black holes were all done assuming a monochromatic mass spectrum. Monochromatic mass spectrum means that you assume that black holes forms in the universe at a given time with a given mass. So basically, all the black holes, all the primordial black holes constituting dark matter, they have all the same characteristics, all the same mass. So when we see these graphs, so what you have to imagine is to take like, to take a line here that corresponds to a given mass, and then you have the corresponding percentage, the corresponding fraction of primordial black holes that would be allowed if all the dark matter was in that particular mass. So again, you had papers in the past that were excluding primordial black holes as dark matter, always assuming, so each study was for a particular mass, assuming that all the black holes had that particular mass. A few years ago, this assumption was challenged, and we started to talk about a wider mass spectrum. In fact, one can even argue that a wider mass spectrum is exactly what you should expect, and the monochromatic mass spectrum is not viable within the formations from the collapse of cosmological perturbations. But so in the moment, even if you had a graph that gave you much more constraints, like the graph that were circulating in the past, the moment in which you assumed that you could have different masses, so you could pile up a fraction of primordial black holes equal to 1, summing different masses, summing the contribution from black holes of different masses. So this comes as a way in which you can make primordial black holes more viable. And indeed, this is what happened also with respect to the perception in the community. On the other hand, one should be very careful, because in the moment in which you widen the mass spectrum, there is also a change in the way in which the constraints should be put. So here you have two different diagrams, one in which you have the constraints in the case of a monochromatic mass spectrum, and here you have the constraints if you have, for instance, a log normal distribution. So you see that the constraints changes, of course, so you still have the viability of primordial black holes in certain particular regions and so on. But again, so something that I want you to appreciate is that on one hand, there was a change in the perception about the viability of primordial black holes, moving from monochromatic mass spectrum to a wider mass spectrum. But this is not just the solution to everything, because then you have to be careful with the constraints in the way in which you take the constraints again. Talking about constraints, I wanted also to mention the fact that I told you that there are constraints from evaporation. That's another example of constraints that have been changing a lot with time. And here we don't, let me see. So we said that small black holes should have evaporated today, so they are not a viable components of dark matter. Well, my last lesson and the last day will be all about remnants. So the fact that after evaporation, you may still have a contribution to dark energy from the residual object after the evaporation. And so again, you have to be careful with evaporations, because these constraints have assumptions, but these assumptions may be evaded. An important point is that in the moment in which we talk about constraints, we are also talking about evidences. So constraints and evidence are two faces of the same medal. Every time that we consider a constraint, well, in fact, in a sense, we are also, so the non-detection of constraints or the avoidance of constraints is also can be interpreted also as an evidence for primordial black holes. This is something that I think is true not just for primordial black holes, but it's true in general, and it's something to reflect upon in this school. So we discussed already different evidence / constraints. There are many that can be studied. One that is particularly dear to me is, for instance, to use not just gamma ray burst, but also fast radio burst, that are a relatively new class of cosmic rays to study the presence of primordial black holes. But I wanted to focus on a few main surveys, a few main studies that, again, I think they can be both seen as constraints and evidence. And the most important one to start with is microlensing. So if I take this diagram here and I just consider only the constraints that come from microlensing, so these are the constraints that I obtain. You see that, these are all different experiments, different telescopes, different surveys that have been carried on through the years. One of the most recent one is this, I don't know how to, OGLE, and something, so OGLE in particular have been studying specific regions, a specific range of masses that corresponds to objects that have a planetary mass scale, but a mass that corresponds to that of a small planet. So this experiment, this stands for optical gravitational lensing experiment. And what has been observed has been a amount of microlensing above what would be expected. So there are events of some extra lenses, let's say, that have an unknown origin, and what could be creating these lenses? Well, they could be just free floating planets that are not bounded to a star, but they are floating alone somehow in the sky, in the galaxy, in the halo of the galaxy, or they could be primordial black holes of planetary mass. And what is very nice is the fact that these extra lenses that have been seen by this experiment are indeed in a region where primordial black holes of that particular mass are not constrained and are allowed. So again, this so microlenses give us constraints, but give us also a possible evidence. So again, looking at the galactic bulges, this experiment has also detected events that have a very long duration. The longer the duration, the larger the objects that creates them. And again, so these objects don't correspond to possible stars in the main sequence, so there could be evidence of primordial black holes, and there could be black holes that in fact fits with the so-called low mass gap for black holes, so black holes that are just a few solar masses. And finally, regarding lensing, there is also lensing for quasars. Now we know that most quasars present microlensing. So there is this recent work by Hawkins that study whether the observed microlensing could be created by the presence of stars. And the result of these studies is that the probability that the origin of these lenses is by stars is very, very low. So what the abstract of this paper says is that it is argued that the most plausible candidates for the microlenses are primordial black holes, either in the dark matter halos of the lensing galaxies, or more generally distributed along the lines of size of the quasars. So again, microlenses, an important instrument to constrain primordial black holes, but today maybe also a way to look for evidences. Another aspects that we can consider in order to study primordial black holes is the way in which they interact with structures. So they can both disrupt objects that have a disrupting effects on the creation of structures, or as we have seen, they can also be the seeds of structure formation. For instance, the seeds for supermassive black holes that then forms galaxies. So again, we can see, we can focus just on the constraints that are given by considering the influence of primordial black holes on large scale structures, like on the formation of galaxies like the Milky Way, or even on clusters of galaxies. for which the constraints are even stronger. So in particular, an example of how primordial black holes may contribute positively to structure formation comes from dwarf galaxies, in particular a category of dwarf galaxies that are ultra faint. And given the amount of visible matter, they should have expected to be unstable. So again, the presence of primordial black holes that are in this case large could contribute to explain the behavior, the phenomenology for those dwarf galaxies. Regarding structures in general, I wanted to mention also a correlation between different cosmic backgrounds that we observe. So in particular, an infrared background of cosmic rays and a background in the X-rays. The correlation between these two backgrounds could be explained if primordial black holes generates early structures. And so both backgrounds are generated at the same time in correspondence. The most important, so then I come to the most important thing that I want you to remember with respect to the influence, the relationship between primordial black holes and structures. So before we mentioned the fact that all the constraints regarding primordial black holes were somehow removed by the fact that they were done by considering monochromatic mass spectrum. Enlarging the mass spectrum changes the constraint. This is also the case for all the lensing constraints, because lensing constraints were done with the following assumption. The assumption was that the distribution of dark matter, distribution namely of primordial black holes, were uniform in the galaxy. Well, the thing is that we observe lensing we observe the lensing from dark matter in a way that suggests that dark matter clumps. So dark matter is not just heavily distributed like in this way, but they are rather but dark matter is rather distributed in this way with clumps. And this could be again, so first of all, since even distribution was an assumption in all the constraints, now these constraints are not reliable anymore. And so we know that dark matter make clumps. And it has been shown a few years ago that primordial black holes naturally clumps. So again, this could be conspiring in the direction of suggesting that primordial black holes are a viable candidate for dark matter. Okay, and then I wanted to come to gravitational waves. So I have shown you before the fact that there was this spike in the productions of paper in gravitational waves So there is like an exponential increase of number of papers that started in 2015 and it's continuing today. And how do we explain such an increase? Well, of course, we haven't detected directly particle dark matter. So this is also something that decreases our confidence in this kind of models, or maybe may suggest us to try to look for alternatives. But also, of course, what happened in 2015 was that there was the first detection of gravitational waves coming from the merging of black holes. And these black holes were in a site that was somehow unexpected. So people realized that it's likely that black holes comes in all shapes and all sizes in a way much more wider than wilder than what was supposed before. So much more research in this direction. So as we did before, so let's focus extracting from the picture we saw before just the constraints that comes from gravitational waves. Of course, this is not just from the direct detection of LIGO, Virgo and Cagra one day, but is also from the other detection, the other hints that we have about gravitational waves, for instance, from X-ray binaries systems. And I wanted to highlight how the detection of gravitational waves through the merging of black holes, again, can maybe suggest that some of the black holes that we have observing through this merging, these mergers, may be of primordial origin. So we said that stellar black holes forms for masses that are above the Chandrasekhar limit, the solar mass. This means that if you see a black hole that is smaller than that is below a solar mass, this is very likely to have a primordial origin. So what about the detection that we have done so far in gravitational waves? Well, here you see a number of events that may suggest the presence of black holes with a primordial origin. In this case, what we are witnessing are black holes that are in the so-called pair instability mass gap between 60 and 140 solar masses. So and we have seen before that there is also there are also black holes that appear in the so-called low mass gap in this 2 to 5 solar masses. But as I was saying, what is the most interesting case is when you may have black holes that are extremely small, possibly below a solar mass. And so we are not able to observe the merging of two black holes of that size, because this will be outside the sensitivity of our instruments. But what we can maybe see is when we have a big black hole that merges with a small one. And so in this case, we talk about a symmetric mass ratio between the two objects that merge. And we do have indeed examples of merging of these kinds. And as you can see, here we have some events, in fact, 4 events in the LIGO data that may be with objects that are below a solar mass, and so they could be primordial black holes. And primordial black holes of these sites, I remind you, that are in the range in which it's viable that all dark matter is constituted, is saturated by them. Okay, so constraints, but constraints can also be evidences. So we have, depending on your attitude on this kind of models, it may change your perspective on your reading of the data that we are acquiring. So let me conclude just maybe 10 minutes with a discussion and a bit more, if you want, philosophical considerations. So I have shown you, I think I have given you a quite bright image of primordial black holes. So they seems to be a very interesting candidate for dark matter. I told you the feeling in the community have changed a lot through the years, and in fact, beside this growth of paper, there has been an oscillating popularity of primordial black holes in the scientific community. So I'm taking this slide from a lecture by Bernard Carr, in which he's assessing the popularity of primordial black holes since he introduced them. So starting from his own paper in the 70s, and so there was some excitement given by the fact that the phase transition between quark and hadrons may have created indeed primordial black holes of small size, so people were getting more and more excited. Then the quasar microlensing was also making people even more excited. And then some years later, the results of about Macho seems also to support the idea of primordial black holes as dark matter. I remind you that during this period, basically, the papers on primordial black holes were staying regular from something between 5 and then maybe at this point they were maybe 20 or 30. And then again, there were more results regarding primordial black holes forming at the causative phase transition. But then there was a moment in which microlensing constraints were completely killing primordial black holes. And now I hope you appreciate why these constraints were not should not be trusted anymore. But nevertheless, there was so in 2005, if you have asked around whether primordial black holes could be dark matter, all physicists would have said no, because there are these microlensing constraints. And then there was new excitement because of the idea that dark matter could be in the form of remnants or sublunar black holes. And then again, there were more constraints on dynamical, so related to the possible disruption coming from primordial black holes. And then again, this is the part that we know now, in which primordial black holes are getting more and more popular after, of course, the detection of gravitational waves, after the lack of detection of particle dark matter. And so this is a growing trend, hopefully. So primordial black holes seems to have a lot of theoretical virtues. So again, what do we do? What do we ask when we assess a theory? Of course, the first thing you want is empirical adequacy. And I mean, we have seen the constraints. We have seen that primordial black holes may be viable in the sense that they are not constrained, they are not killed by the observation done so far. They are a very simple explanation in the sense that so I started this lecture saying that they don't really require new physics. So you just need gravitational collapse that comes from general relativity. Then, of course, there could be other form of new physics that may be needed. So in a sense, you may argue that if primordial black holes are formed as a result of perturbations that are produced after inflation, well, okay, then you need an inflaton field. So there is new physics in the form of the inflaton field. Or in the case of primordial black hole remnants that I will discuss in the last day, of course, well, you need quantum gravity, but this is all the kind of physics that is expected within our model. Then you can argue opposite to what we were hearing. So do we want for our theories some theoretical novelty, something very specific that works just to explain dark matter and to explain primordial black holes? So, I mean, in this sense, primordial black holes are less exciting, but maybe being conservative could be what we want. We want simplicity. And for sure, there is explanatory power in this kind of dark matter candidate, and we have seen that primordial black holes may oh no, yeah, let me wait. Primordial black holes may span different ranges of masses that would give different phenomenology. So they can explain the excessive microlensing that we see. They can be the seeds of supermassive black holes. So there are a number of different phenomena that can all be explained assuming them. So why people was not working more on them? Well, there is certainly a component that has to do with the sociology of science, the sociological factors in the development of scientific theories. So when I say there is a simplicity in assuming primordial black holes as dark matter, but if you are a particle physicist, maybe you want to use dark matter to support some exotic models with new particles, and historically, of course, the community of particle physics has been much more powerful in terms of human resources and also in terms of fundings than the community that comes from general relativity, from which primordial black holes comes, if you want. There is also maybe a less polemic take on this, in the sense that the problem with primordial black holes is that they were too good to be tested. So they were a perfect candidate, but at the same time, especially in the past, there were not really experiments that could have proven or could have falsified the presence of these black holes. So let me remind you, where do I had a, just wanted to, where is it? Oh, this one, yeah. Let me give you an example. So, no, sorry, this is not the slide I wanted, this one, yeah. So let me give you an example of how many primordial black holes you need in case they are dark matter. So let's take the simplest case in which you don't have many different kinds of dark matter. Let's suppose that all the primordial black holes constitute the dark matters, and suppose that they have a monochromatic or almost monochromatic mass spectrum picked at a moon size black hole. So the size of these objects would be 10 to the minus 8 centimeters. That is basically like a nanoparticle. Can you imagine? And then, so like you squeeze the moon to something that is smaller than a virus, and then you want to know, so you know how much dark matter there is in our galaxy, and so you will have something like 10 to the 25 of them in our galaxy. So, but this means that in our solar system, you may have just a few of them, and this will constitute all the dark matter there is. So you may have in the solar system, you may have suppose that they were kind of evenly distributed. Well, they will be at a distance that is above 10 astronomical units. So like the distance between the Sun and Saturn, that is quite far away at the periphery of our solar system. So this means that these objects are extremely rare to observe directly. So in our solar system, we have just a few of them, let's say 4 or 5 of them. And it's only when we look at the collective behavior, we look at faraway galaxies, and we look at microlensing, that we can have hints of them. But these kind of hints are coming now as the technology advances, as new experiments are made. But so in a sense, I wanted to excuse the fact that it was much more efficient just to go by brutal force and try to detect new particles than try to prove primordial black holes, because even if they were a very appealing explanation for dark matter, they were very, very, very difficult to prove.
For example, Pluto planet was discovered in this way because it was perfectly in the orbit of the external planets. So if you have 10 more objects like the moon inside the solar system, they should be visible around, at least in the entire. We know with the high precision the orbit of the planet.
Yeah, no, I understand. Yeah, of course. I mean, this is an object like Pluto, so we have detected Pluto. Again, you have one object like this sorry, by the way, so it's not so
you say, yeah, it's possible that
look, so suppose you have an object like this within the orb cloud. So how do we distinguish this? And keep in mind that you don't see it. So if you have yes, I agree. So, but do you have control on all the objects that are in the orb cloud? We don't observe them. So we didn't know how far our solar system was extending until 5 years ago. I don't know if you realize this. Yeah, I mean, if we have one of the objects in the orb clouds that is one of these primordial black holes, well, how do we distinguish this among all the others? Again, you don't see it, so.
Okay, we can do the following. We know the sample with acquisition up to the blue door. We can take this three-dimensional model.
Yeah.
We can put that up because inside this, I don't think that this is an object like that. It should be this. Okay, so that I would add is if we have 10 to the power of 11 stars and 10 to the power of 25 primordial black holes, that would mean on average there would be like 10 to the power of 14 primordial black holes in our solar system. Or like,
well, again, keep in mind the fact that they cluster, by the way. So you will, of course, the dark matter profile within the galaxy is to have more of them within close to the galactic center, and then less and less.
On average, 10 to the power of 14 black holes per star, even though they are not distributed that way, but very more close to the center. But that would still be probably way more than just one or two objects in our solar system, I guess. So you have huge, or let's say closer to our solar system than to the next. We'll call it that. Okay. And it's much more than 10. I mean, yeah, if we have a couple factors of 10 objects relatively close to our solar system, I also think we should be able to stand out.
Okay, so keep in mind the one thing. So this is to give you an example of estimates. Something that I was telling you before. They could be, so this is in the case of a moon-sized object. And we are making this simple calculation for a monochromatic mass spectrum. But we just said that probably the spectrum is not monochromatic. And also it's not impossible that we can have very, very small black holes and very, very large black holes. So this makes these estimates much more difficult to be done. And I was telling you that even we were even considering, so when we look at the constraints, where is it? No, not here. Where do I have it? Here. So remember that there is also, okay, so this is not changing, I don't know. Okay. Yeah, so what you can see, so there is still the possibility that we can have some objects that are even extremely large. So even just one per galaxy. So again, my point here, so I'm sure, I mean, of course we do micro lensing, we do studies, but I think that is a kind of objects that are quite elusive. Yeah, so sorry, Piero.
I think that the kind of direct dynamical constraints that you're are included in this kind of law.
Absolutely.
One line which is through there and is labeled WB, which means wide binaries. So you need a system which is extremely stable from the dynamical point of view and extremely loose. Yeah. So these are stars which are in a binary system and are sitting very far away one from the other, a couple of parsecs one from the other. And then if you have a black hole that comes in, can make a curve that orbit in such a way to divide the binary. And that's the best you can do with direct dynamic constraints. All the others, in all the other ranges, there's something else which does better.
Thank you.
You can complete them also with the planets. Because sometimes
I'm telling you, the exoplanets, there are a series between things which keep you all the time. So that's not so relevant to consider.
Yeah, so I think this is to conclude. I think it's time to close now. So I just wanted to conclude with a consideration regarding what does it mean to falsify a theory, about the fact that we have to be extremely careful with constraints. Constraints always come with assumptions, and in particular for primordial black holes, assumptions such the fact of having a monochromatic mass function that has been now replaced with an extended mass function, and the fact that when we consider lensing, we should not assume in a very simplistic manner a even distribution of objects, but we understand now that dark matter clumps and primordial black hole clumps too. So it's very difficult to falsify. So we have to be careful in claiming a falsification of a theory using constraints. And constraints are dual somehow to evidences. So microlensing and clumping are themselves maybe a sign that can be interpreted in the future as an evidence. So I think this is all I wanted to tell you today. Tomorrow I will continue, well, not really recent developments. So I think I wanted to discuss more about what are the different mechanisms for formations of primordial black holes, give you a bit of a flavor of the different options, and some more popular. So in particular, just having inflation and having the production of primordial black holes from the perturbations, the cosmological perturbations produced after inflation. There are also other possibilities that are more close to my heart, like having primordial black holes coming from a bouncing cosmology. So this will be the beginning and the end of the next lecture. And I think this is all for today. Well, I think it's time to go to eat, but of course I am available anytime for questions, short questions now, questions at lunch, or maybe questions tomorrow when we resume.